All right, welcome everyone to Robotics and Artificial Intelligence Meetup number 39. As some of you have been attending the previous sessions, you know that the theme for this month is soft robotics, and we have discussed various aspects of soft robotics in the previous sessions. Last time we talked about machine learning for soft robots, and we had an overview of different machine learning approaches that are being used. And before that we talked about Baymax, and in the first session we just had a broad overview of different kinds of soft robots that are used commercially and also for research. So today we'll have a very special session, and the theme for the session would be design and control of soft robot hands for dexterous manipulation. The agenda would be, after this introductory presentation, the main topic will be presented by our guest for today, which will be followed by a Q&A session. And after that, we can have introductions and casual networking as well. So what are we doing here? So basically, we are an active learning group of robotics and AI enthusiasts, and we meet every single week and discuss about one particular aspects of robotics or an AI application. And we believe that the best way to learn is to actually learn from case studies or projects that have been implemented by someone, and that is how we try to do it here. There are a bunch of roles that you can take up on the server. You can check the assign roles channel, and there are all of these roles which I'll not go into detail of. If you want to participate actively on the server, you can take any of the different roles that are available. And we are a volunteer driven community, which means that anyone is free to share their project or idea or any experience that you want to share. And for that you have to go into the Meetup volunteer channel if you want to volunteer for a meetup, and or a paper reading volunteer if you want to present a paper specifically. And everyone can participate regardless of experience or age, so we want to keep it accessible to people from all age groups and backgrounds. One important point to make is that the meetings would be recorded and shared online, so if someone doesn't want to be want their voice to be included, you can just message me and I'll edit that out. That should not be a problem. So that's it from my side. Now I'd like to introduce the guest for today, who is Dominic Bauer from Carnegie Mellon University. He is doing his PhD in the area of soft robotics, and I think you guys will enjoy the theme that he'll be discussing and the ideas that he'll be sharing today. So Dominic, now over to you.
Right. Thank you. Yeah, thanks for having me. I'm very excited to share some of my research with you. I'm just gonna start sharing my screen here. All right. Maybe I can get some feedback whether you can see my screen.
Yeah, we can see your screen now.
Okay, great. So again, as you already, I already heard that you talked about soft robots before this month. So today I'm gonna talk specifically about soft robots for manipulation. And we're gonna cover quite a lot of different topics within soft robotics, and specifically for dexterous manipulation. So if you have some questions throughout my presentation, feel free to just ask, and maybe we can discuss it, and I can give some more information if needed. Right, so let's start. Maybe you've seen the video in the announcement, but I'm gonna show it here one more time, just so that everyone is kind of on the same page what these robots are about. as you can see here, these robots are some of the robots that we build are very human-like. They look very human-like in terms of their motions. Some people usually, when they see them the first time, they say that they get some uncanny vibes because they kind of look so natural, and I definitely agree with that. They sometimes kind of looks a little bit creepy even. But yeah, we can do a lot of really cool grasping manipulations. We can pose the hand in different poses, and so yeah, these soft robots that we're building, I think they can do really cool things in terms of manipulation. And that kind of brings me to like the main topic of all of the research that I'm presenting today. In general, our lab always builds robots that are safe, that are inexpensive, and that are customizable. And with that, I mean safe. We talked about this with, for example, it's the same, follows the same idea as Baymax, where you have huggable robots, for example, and then the same idea goes for our robots, where you have a foam robot which is really soft and squishable, and you can hug it, or you can touch it, and you don't have to be afraid of getting hurt. Then, in terms of inexpensive, we think that robots need to be cheaper so that everyone can technically afford a robot, or that you can maybe build the robot at home. And then customizable. We think that robots in general should be, if you say, no matter what your task is, whether you want to put the robot hand on an humanoid robot, or whether you want to put it on a industrial robot arm, or whether you want to use it at home or somewhere in a factory, you should be able to kind of quickly customize the robot hand to do the task that you wanted to do. And so these are basically the main three topics that the kind of, you can see these ideas everywhere in the research that I do. And so let's have a look at the capabilities of these foam hands. We already talked about secure grasp. So here you can see like a wide variety of grasps. For like in the top left, you can see basically like a precision grasp, where it's just using like the fingertips to hold the object. But then there's also a bunch of different power grasps, and yeah, you can get very stable grasps if these hands in a really easy way. Another thing is you can make gestures, you can pose the hand. Then grasping, here you can really see how the hand kind of deforms with the object, and kind of envelops the tennis ball, which really helps with grasping. That really helps with creating this very stable grasp, because the hand is so compliant that you get this very strong force closure around the object. And then of course, what I really like are in-hand manipulations. You can, all of these videos are recorded doing open loop keyframes, replaying open loop keyframes. You can see even just without any feedback, you can achieve really dexterous manipulations. Right. So let's talk a little bit about what are these hands made of. What is the difference maybe to a rigid or traditional robot hand? These foam hands have a foam core. In terms of foam, we're talking about polyurethane foam. So something like a foam that you can also find in a mattress, for example, or your pillow, or in a car seat. So those foams are generally very cheap. They're available, and the easiest way to create a foam core is to simply create a mold, a silicon mold, as shown in the bottom left, where you can use your own hand, for example, to create a blueprint and then create a silicon mold and create this foam core. And once you have that foam core, you can cover this with a textile skin, as shown on the right. And then we sew tendons through this textile skin. And we can actuate those tendons by just using servo motors. And then similar to a human hand, where we also have tendons that actuate our fingers, when you pull on the tendon, this creates like a contraction or a deformation of the finger. And the big difference here is that, again, there's no internal structure. It's just a foam core, so everything is completely soft. Whereas, for example, in our hand, we have bones and we have joints and we have links. And so that's I think the big difference here. And that also leads us to, or that also comes with a lot of challenges, actually. So the problem with that is that there's not really a standardized process of designing these hands. Because you don't have bones, you don't have joints, or you don't have links, it's very hard to really predict how the hand will behave once you build it, in terms of what deformations it will undergo. So the only way to really predict, or the only way to know what your hand will be able to do, is to actually build a hand and then try out different tendon contractions and then different tendon placements. And that is because, again, it basically has an infinite amount of degrees of freedom, which makes it just really hard to model, really hard to understand what is going on beforehand. But again, that comes with the benefit of having just an enormous amount of compliance, and you can do these really cool manipulations just off the bat. All right, so in the next 50 minutes or so, I'm gonna talk about a bunch of different things. I'm gonna specifically focus on those four main areas: design, fabrication, modeling, and operation. I think since everyone here is interested in learning something about soft robots, I think it's good to just kind of, for you to get an overview about the different problems that this goes for every soft robotics system, so to say. I'm gonna specifically show you this in terms of foam hands specifically, but I will go through these problems with you, and I will, towards the end of the talk, I will spend most of the time on the interactive and automated design process, because that's what I'm most interested, I guess, in my PhD studies. But let's start with modeling. We already talked a little bit about manual design and manual fabrication. So again, the easiest way to design these hands is by really just taking your, as a design, just using your own hand, using that as a blueprint to create a cast, and then fabricate the hand as I described earlier. So in terms of modeling, you might ask, why do we even need to model soft robots? What's so important about that? I think all of you, or at least most of you, have some background in robotics, so I'm sure you all know about forward kinematics and inverse kinematics, and that's a great concept. I think it's very helpful to be able to do forward kinematics. So the challenge always is, right, I have an end effector on a robot arm, or I have a fingertip on a hand, and I want that to go into a certain position. and then basically to first find the position of the end effector, you can simply use the link lengths and the joint angles to basically do your forward kinematics to determine where the end effector location is at that point. And then if you want to move somewhere else, you can use inverse kinematics to find basically the joint angles that can give you that position. And that's a very powerful concept, although it's fairly easy. And it with soft robots, the problem is we can't do any of that, and that hurts us in many cases. It hurts us a lot because if we have, say, some soft material allocated here, and we put a tendon on this material, and we contract the tendon, we might have an intuition of what will happen, but there's no way to really predict what is going to happen exactly and where our end effector or like our fingertip is gonna end up. So, and that is because basically the material can deform in any direction. It technically has an infinite degree of freedom. So really, the only way to combat this is to do finite element simulation. There are some other ways to model this in the literature, but what we mostly do is we use Fva analysis. So I'm not gonna go into the details here, but I'm just gonna like basically, if you have an actual robot hand here on the left, and you know the 3D geometry of that hand, you can discretize that into a tetrahedral mesh, and you can place tendons along this mesh. And once you contract, so the goal is here to, do you want to know how the hand deforms based on a tendon contraction. And the way to do this is basically you have different energies in that system. You can think about this as kind of like each of those edges in the mesh acts like a spring, and then also you have the tendon is also acting like a very stiff spring. That's the energy here, and then you have springs that connect the hand to the environment, and the energy stored in those is the energy E boundary. And so all of those energies stored basically in those springs summed up is the total energy. And once you contract the tendon, you can find the deformed solution by minimizing the total energy. So basically, you're just gonna try to solve you're just basically trying to solve that system for the minimum total energy and energy equilibrium state. And that gives you this deformed pose. Yeah, whoever is interested in that in more detail, we can talk about it, or also you can read these two papers that we published where we explain this in very detailed way. Another part with soft robotics, in addition to deformations, we also have soft body contacts, meaning that since our robot is soft, everything that we do is soft body interaction. So I know a lot of you might have already worked with soft body contacts where they try to grasp soft bodies, they try to or soft objects, or they try to manipulate soft objects. Whenever we do something, it is always soft body interactions. So basically, this always means trouble because you're basically the body that we're actuating can deform. So it's very hard to detect collisions. And this is still open research. I felt like since this is a very big problem, I just wanted to give you like a quick idea of what we did to try to simulate some soft body contacts. That's a very simplified process of how to do it, but it kind of worked for us, at least to some fairly well extent. So basically you can solve for the FEM body for the deformation. Then in the second step, you detect whether your whether your hand or your finger is in contact with a rigid object. When you detect a contact, you take the nodes that are penetrating, excuse me, penetrating the rigid body, and you're pinning those nodes back to the rigid mesh. And then you apply a force inversely proportional to the distance that this node penetrated the mesh. And then you have to solve one more time to kind of incorporate those contact forces. And we can at least get an idea of what interactions with the hand look like. On the left here with like a ball, or we can try to grasp something. But as you can see, it's still very unstable. You have a lot of jittering because if you solve if your time step gets too large, your objects will penetrate the FEM mesh by too much, and then this gets unstable. If you lower the time step by too much, the simulation will get extremely slow, and there's really no like so there's a really big trade-off, and this is still problematic. There are some open source simulations out there that can do that try different other approaches that are a lot more sophisticated, and they work to some extent. But the general problem that I found was that all of these softwares, even state of the art, are still very, very slow in terms of simulating, especially soft actuated bodies and contacts. Right. So what can we do with this kind of simulation? I think let's look at control a little bit.
Dominic,
Sure.
before we proceed, I just wanted to ask if anyone has any question, you could also ask in between, right?
Yes, please. Yeah.
Hello. So
Hi.
I'm Shaurya. So how do we simulate everything? On which software we do these simulations?
So the simulation that I showed is custom. So the framework that I showed here, that was created by some other students and some other professors. But there are other softwares to use. For example, the one I show here, that's called Fva framework. That's an open source framework. I would say that that's probably that's probably the framework that I would go for if I would start with simulation for soft robots. Does that answer your question?
I have a question. I am Apoorv.
Yeah.
Did you mathematically model slip in your? Did you incorporate any kind of slip in your model?
No.
You're estimating only the contact forces, or calculating
Yes. Again, that's a very simple approximation. I think the goal for us is to really have something that runs as fast as possible, so we can do learning. The idea of so for us, we don't care too much about slip in that case, because again, as I showed in the beginning, stable, like robust grasps or stable manipulations aren't the big issue for soft robots. I mean, of course we would love to be able to model that, but I think that's not the biggest or like the main priority for us.
Okay.
So yeah, I think that's, if you want to model slip, I think that's mostly interesting for maybe rigid robots where you kind of want to, So I think that's again, that's one of the benefits of using this soft these soft materials. You get this compliance from the material, which then really helps you with stable grasping. You have very minimal slip. If you have slip, then some other, so say you have some slip in one finger, then the other fingers will maybe deform a little bit more, and then we'll close the grasp again. So it's kind of yeah. There's kind of this underlying low-level control that the material takes care of itself, and I think that's a pretty powerful tool. Yeah, great questions.
Yeah,
All
thank
right,
you.
so
Thank you.
yeah, yeah. So we tried. So basically using our custom simulation framework, and also looking into SOFA, which is an open source simulator. And I spent a decent amount of time to look into different simulation frameworks over the past years. And the task here is to basically learn how to actuate tendons to push a cube just into into the red circle here on the left. And it can learn that fairly well, but this is already this already takes quite a lot of time, because it's very it's actually a more difficult task than it looks like, because you have a highly underactuated system here. So with just 3 tendons, you can create very complex motions. And overall, I think what we found is that for more complex manipulations, especially in-hand manipulations where you need to hold the object in hand, and it's very, very difficult to simulate that, because as I showed earlier, those objects typically tend to get unstable, and you kind of get these jittery motions of the object. So here, just to show on the right, like that's where the policy is still exploring some random actions and kind of just like trying to touch the cube. But overall, these simulators all share the same idea of solving an FEM mesh and then using some sort of soft body contact model to solve for the interactions between hand and object. So a little more straightforward approach of controlling soft robots, but also, I mean, in robotics in general, teleoperation's been around for a long time, and the idea with teleoperation is that basically the robot mirrors basically what you do in some sense. So in this case, our goal was to have the robot mimic our poses, and we can use our hand to control the robot pose. We implemented that using a cyber glove. The cyber glove has some resistive bend sensors, and that give you the joint angles of your hand. And what we did is basically post the robot into a certain pose, and then we mimic that same pose with the cyber glove. We record 24 poses each 5 times, and then we can learn a kernel ridge regression model to map from this 22-dimensional space to the 10 tendons that we have on the hand. And that works really well, even though it's a very simple approach. It works well to just kind of pose the hand into different poses. Of course, the poses don't match 100%, because again, there's like this discrepancy between having joints, having links in our hand, and having none of that in the robot hand. So the motions that we can get with these foam hands are sometimes different from what we can do with our human hands. And then turns out you can even manipulate objects using that approach. But this is actually pretty hard, because you don't really have tactile feedback. So you can't, I mean, obviously you can't feel, you don't get any feedback from the object that you're touching. And then that just makes it incredibly hard to do that. And that brings me to the next point. With soft robots, it's often a problem to incorporate sensors, because just like the robot itself, your sensors need to be really soft. And so that already is a pretty big constraint on the sensors that you can use. And then so the robots that I showed so far don't have any sensors, and that's also why you can't really get any feedback, or that's why all of the control that we did is always open loop, because you can't really close the loop without any sensor feedback. I'm just gonna because I think that's one very interesting part of soft robotics still, where there's a lot of work to be done. I'm gonna talk quickly about two different types of sensors that I like. There's more sensors, but I'm gonna talk specifically about capacitive sensors and magnetic sensors. So in terms of capacitive sensors, there are basically, the idea is that you have a capacitor, and when you touch, it's similar to what you have in your phone, in your display, your touch screen. So when you touch the sensor, the capacitance changes, and you can sense that, and then from that you can get forces, and you can also get like distance from your finger to the object, from your finger to the sensor. And the idea is here to fully print that sensor. So you can use conductive filament and print the top and the bottom layer, which is acting as an electrode, and then you have a center layer from a non-conductive material that acts as a dielectric. And yeah, so you can see down here, this is my finger, and you can print these even smaller. So you can get actually really small sensor sizes, and they're also, the nice thing about these is they're like really flexible. So we're currently working on getting those onto soft hands, and then basically close the control loop and get some sensory feedback from the hands. Another type of sensor that's interesting is magnetic sensors. Most of you might have heard of these soft magnetic skins, or like artificial skins. And so the way these work is you have a magnetometer, and then you have a skin, like typically it's maybe like a silicon or some polymer, or like a foam skin, which has magnetic particles embedded. And then when an object or when something penetrates that skin, the skin is deformed, and with that the particles move, and that movement of particles creates a change in magnetic field, and you can sense that with the Hall effect sensor. And the cool thing about that is that you don't only get normal forces, you can also get tangential forces from that, or shear forces. So that's generally a very powerful way to sense deformations or contacts with soft robots. One final point in terms of operating soft robots, and specifically our foam hands. People usually like to ask, how long do these hands last? Like, are they even durable? Can you use them over a longer period of time? So we kind of wanted to see how many actuations can we get from a hand like that. And so we actuated this 10,000 times, and did some motion tracking to just evaluate how does the motion of the hand change over time. And turns out it changes a little bit. So one big problem in soft robots is that because you use very soft materials, over time you have you tend to have hysteresis effects, meaning that your material changes the behavior, changes its deformation behavior. And we can observe some of these effects, but overall, after 10,000 trials, there's only a drift of about 1.3 millimeters after like an initial. So after an initial break-in period sort of you really don't have too much of change in the deformation. And in addition to that, we were also happy that this actually can do 10,000 plus deformations. And so, yeah, I think that it's fair to say that these hands are really a lot more robust than they look. I think if you look at the hand the first time, you might say, "Oh, this kind of looks self-made, homemade," and that's definitely true, and that's kind of the whole idea of that. But that doesn't really contradict with the hands being very durable, or that you can use them for a long period of time. All right, so I think if you have questions to the topics that I just covered, then now would be like a good time to ask questions. Otherwise, I would start maybe covering like more in depth the design process.
I have a question.
Yeah.
Is there any kind of planning involved before grasping the object? Like, what kind of grasp you would be hoping for? Like, the geometry of the object can be conformal or non-conformal. So, what fingers should be and where should be uh, localized? That is one of the main issue.
Yes. Yeah. Good question. So in terms of the graphs that we showed, so all of those graphs are keyframed, meaning that we predefine a pose, and then we just close. So for a given object, you can, for example, predefine a grasp.
Three graphs are defined.
And yes, yeah, and so you can so one of the I will get into that now. Basically, that's also one of the reasons why I was talking about like modeling in terms of deformation and context. So one way to find those grasps is to do it on the actual robot and do it by trial and error. The cool part is, again, once you did it for one object, it repeatably works for the same object, even if you have slight variations, right? So that's the benefit of having a soft body. But of course, that's still somewhat tedious to do this for every single object. So the idea is, if we can model the deformation of the soft hands, and we can model at least to some extent the contacts between objects and the foam hand, then we can in simulation already look for keyframe poses, basically. Right. I think this is a great question. I think this kind of ties into what I'm going to talk about next. So yeah, in order to be able to grasp an object, we need to find these poses, or we need to find specific keyframes and actuations that actually can grasp an object, and that's actually harder than we initially thought. So the question here is, where do you need to place the tendons on the hand in order to be able to create a certain type of motion or deformation? And so we created this kind of interactive framework where you can, if you have a hand morphology, you can place tendons, and then you can kind of explore how the hand will deform based on where you place the tendons. And this is really useful because that way you don't have to actually build the hand each time and kind of iterate on the actual robot, but you can really try out new tendon routings in simulation first and really kind of explore the workspace of the hand, see if you're happy with that. And yeah, and also kind of at least get some idea of keyframing motions before you actually do them on the robot. So you might say, well, this doesn't look very difficult. And we also thought that with that, we should be able to get really, really good results in terms of creating different poses. So the problem is that it's actually quite hard, and we had some other people try that out that don't have soft robotics background. They which have all of them, I think, had some robotics background, but no soft robotics background. And we asked everyone to, if you say you want your hand to be able to do a certain pose in order to grasp something, how do you need to route the tendons, and how do you need to contract those tendons to get to achieve that kind of pose? And so the idea was that for each grasp, everyone had 10 minutes to find a tendon routing pattern. So in like this gray overlay or this translucent overlay, that's the target pose, and then you can place some tendons, you can contract them, you can like see, okay, what's the resulting deformation? If you're not happy with it, you can like place another tendon, you can place up to 10 tendons. And you're trying basically to match this like dark overlaid pose as closely as possible. So then later on the real robot, if you know your tendon pattern, you can kind of create the same poses and grasp this object so it turns out that some people are better at this, some people are worse at it, but in general it's quite hard to get reliable and like consistent results for different types of poses. So in some cases, some of the fingers were off by like a huge margin, like far more than 1 centimeter, which, even though the robot is very compliant, like if you're off by more than 1 centimeter in terms of your fingertip position, then it tends to get very difficult to grasp correctly. I would say generally, if you're like below 1 centimeter, that's about what the foam can kind of what the foam can still cover by just like deforming a little bit. So as long as you're like in the range of 1 centimeter off from your target, then the robot will still be able to deal with that easily. And that kind of took us to like this whole idea of, oh, can we further automate the design process? Because finding tendon routings and finding contraction patterns turns out to be more difficult than we thought. So now I'm gonna talk a little bit about like tasks and designs. So what do I mean by tasks? In general, tasks could be anything like a either pick and place task or some in-hand manipulation tasks, or any kind of task that we do to sort of reorient objects before we grasp them. Anything we do in daily life. And then a design typically is characterized by material, shape of the robot hand, actuation, say like in terms of what kind of motors or what kind of are you using, tendon actuation, are you using like a direct drive, or are you using pneumatics to drive the hand, and then how do you control that design in terms of like using a PID controller or using something more sophisticated like a neural network. And typically what's done today and what's still mostly done is, if you have a task that you want your robot hand to do, you go out, you design in CAD, maybe you design a robot hand, or you design a robot. You select the material, you select how many fingers the robot should have, how the robot should look like. You select motors, inspect those out, and so everything that we currently do is entirely done by humans. But the question is, could we automate that process? Could we improve that process? And could we find better designs and improve like the capabilities of robots in general by automating this process? So in terms of foam hands, I'm going to talk about this a little bit now. So a foam robot, or also a soft robot in general, the most, or like the basic and most important, or one of the most important aspects of a foam robot design is the hand morphology. So we're talking about how many fingers does that robot have, how long are those fingers, what's the shape of the palm, how thick is it, and that basically predetermines already what kind of motions, what kind of grasps you can do, what kind of manipulations you can do. Then the second important part is the rest shape. That might be non-intuitive and non-obvious for a lot of you. So you can have the same morphology in terms of finger lengths, but you can have different initial configurations where the foam is basically, for example, in the top, like a cupped rest pose, it might be more difficult for the fingers to go into a flat position, whereas in the bottom, it might be difficult for the fingers to reach to go into contact with the palm. So not only the morphology, but also the rest shape then predetermines what your hand will be able to do. Then a third point is the tendon routing. So where do you have tendons run along the skin, and where do you place them? How long are they? And that also, of course, has a huge impact on what your hand will be able to do.
So
And then finally,
one small question.
sorry.
How are the tendons embedded with the foam structure wise?
Right. So in simulation, they run along the mesh, along the edges of the simulation mesh. But in the actual world, we sew them through a textile glove or a skin.
Okay, so through an outside a membrane or layer.
Yes. Yeah. Mm-hmm.
Okay, got it.
Yeah. So you can you can basically do arbitrary tendon routings along that outer layer, and that's pretty cool because that as you can think about it, you're not really constrained to say tendons that run straight down on your finger. You could place them, as you can see here. You can place them in a wild, like you can place them really like whatever you want. You can place them.
Yeah,
And
so
create, like,
offers like
arbitrary.
more flexibility.
Sorry?
Yeah.
Yes. Yeah. Yeah, and then finally, if you place those tendons, you need to find a good level of like contraction to create like either poses, or like if you sequentially move through different poses, then you kind of can create motions. And so in terms of if you want to automate this design process further, one thing that we always need is we need to be able to record, or we need to have some sort of optimization target, or we need to know, like we have to have a representation of what we want the hand to do. And that is actually not a trivial problem. So what we did is we used the cyber glove that I showed earlier to record joint angles, and we recorded poses of the human hand for different grasps and different objects. And the way we do this is we record the pose of the human hand for a variety of different grasps. We transfer this pose to the simulated robot hand, and from that we extract the fingertip position and the orientation and use that as like a target for optimizing. In this work, we fixed basically or predefined the morphology in the rest shape simply because it's incredibly difficult to optimize on a 3D geometry or a 3D mesh. It's we found that to be extremely difficult. So we started out with predefining that, and then by using these recorded poses and using a predefined morphology and rest shape, we're trying to find tendon routings and contractions that can give us stable graphs and stable or can give us poses that we want. And in terms of goal poses that we use for optimization, there's for the ones of you who don't work with manipulation, there's taxonomies that kind of classify graphs into different categories. And there's the two main parts are power grasp and precision grasp. And within that, there's like a few different other categories. And the idea is here to kind of capture the whole variety of different grasp and manipulations humans do. And so we kind of wanted to cover as many different types of graphs as possible. So here you can basically see some power grasp examples. And then here you can see some precision grasps. In the left, we always recorded the object with the cyber glove for like a ball or like a finger, like a pen, and like a box or a cup. And then on the right, you can see the transferred pose in simulation. And when you compare basically the designs that we find through optimizing for tendon routings and the designs that are created by humans, you can see, so here on the left in the first column, you can see target poses that we wanted. In the second column, you can see the results that our user study participants were able to get. You can see there's like a large variation in designs that you get. So it's very hard to find a consensus between human designs, and that kind of like, we generally don't want that, right? We want, like, I think ideally we would have like a somewhat like consistent result and somewhat consistent design. Then in comparison to that, you see so some of the users did a really great job. So in column 3, you can see the results from the best design, and then you can see the optimized result. And in column 5 and 6, if you look at the mean distance error of the individual like mesh vertices, you can see that some, especially like the distance error in some of the fingertips for some of the graphs is really large for human designs, whereas except for maybe the pinky in the optimized result, that there's like those match fairly well and generally are below like this threshold of maybe 1 centimeter. So now the important question in robotics, I feel like, is always, will this work on the real robot? And so you can do a lot of stuff in simulation, and then the question is always, can we actually do it on the real robot? Does it work? Can we transfer it? And so in terms of poses, at least if you look at it qualitatively, we can match those poses fairly well, even though it might look like, to someone who doesn't work with manipulation, these might look fairly similar, and they do in some sense look fairly similar. But if you want to actually grasp the objects, so we can replicate some of these graphs very well. So for example, like this precision tripod, we can replicate that, or holding a pen, that also works. The problem is that there are certain cases where this doesn't work either at all or doesn't work very well. And this is in part, again, one of these typical problems that we always have with sim-to-real. But one problem there is also that the way we formulate our goals for optimizing the tendon routing is not sufficient. And so what we did is basically we use discrete static poses, and these poses don't have enough information about contacts or contact forces, contact patches, contact areas with the object. So in some cases, it's just not enough to, on the actual robot, then create a stable grasp or even do a manipulation. So what do we need? Ideally, we want to have information about contact areas on the object. Why didn't we do it in the first place? Well, that is quite challenging. So the problem with contacts is that contacts change all the time. When you do manipulate an object, they move. When you rotate the object, the contacts move on the object. Maybe you're gating your fingers, meaning that you move your fingers, you remove them, you place them somewhere else. So this is just really hard to track. Then on top of that, you typically can't capture those with vision because you always have some occlusion. And even if you have a glove that gives you the tactile feedback, it's hard to reconstruct it because it's only giving you the tactile feedback on the hand, but not on the object. And yeah, most of all, like the human hand is very complex. So getting contact information is really challenging. So in our newest work, most recently, we looked into this. How can we get contact areas? So why are we so interested in that? I think that the main part is really that contact information encodes some implicit information without really making any assumption about the manipulator. So if you have the contact information of a manipulation over time, this information is independent of the manipulator, meaning this could be applied to any anthropomorphic, non-anthropomorphic manipulator. It could be applied to a traditional robot, a rigid robot, or a soft robot. And so the information that is encoded in these contacts is just very rich, and it's very it doesn't make any assumption about the manipulator. And the good thing is that in order to capture contacts, we can use a similar approach that another group at Georgia Tech developed 2 years ago, and they use a thermal camera to expose the thermal trace of a hand on an object. So here you can see basically the thermal trace a human hand leaves on an object, and they can reconstruct that and get basically contact patches for static grasps.
And Dominic, you mentioned that these contact points that we get, they are independent of the manipulator that we have, or did I mishear that?
Yes. So of course they're not independent. So they're not independent of the manipulator that we're using to record them, but this information doesn't, like, you can transfer that information to another type of manipulator, for example. Even if you record this information with your human hand, the areas of where you make contact, you could replicate those areas of contact with a completely different hand, or you can use a rigid robot hand to replicate these areas for grasping, or you could use a soft robot. So it's kind of you use your, of course we're interested in what are humans doing, because we're so good at it. We're interested in, we want to know, where do we make contact, what do we do, how do contacts move, to then use that information to design or to design control policies or design new hands. But those are then detached. Those don't necessarily need to look like a human hand. They just need to basically,
so they're
that capability.
So they're then transferred to a different type of manipulator used for that different approach then.
Well, yeah. So at least that's definitely the idea, and that's what we're hoping to do in the future. So I think, again, what I'm showing now is, I guess, most recent work. So again, the initial work we did with optimizing for new designs was, it was obviously not enough in terms of specifying the goals so we had to go back, basically find a better representation. We need to find a better representation for manipulations and for tasks. And so this is basically what I'm showing right now is specifically if you want to achieve, if you want better information about dexterous manipulation, or if you want better information about contacts, for then going out to either design new manipulators or designing control policies, this is kind of our a way we're trying to move forward from here.
Yeah. Okay. Thanks. Yeah. Thanks, Dominic.
So yeah, what's the difference here in terms of approach? Generally, it's a similar approach to the thermal imaging. The main difference is that thermal cameras are extremely expensive. So if you want a thermal camera with a decent resolution, you're in for about $10,000. Plus, you have to go and calibrate and register, or like you have to do calibration and registration, which is also very tedious. We found this very cheap paint or pigment online that you can just coat objects with, and then you can expose the same thermal signature to the human eye and also to cameras. So basically, we're coating objects with this spray paint, and then we can capture this with, for example, a real sense or just any camera, any standard camera, which is substantially cheaper, and we don't really need to do any calibration or registration. We can just use that straight off the shelf. So you might be interested in how this looks like. So right after we make contact with an object, the thermal trace is still very visible, and this is fading fairly quickly after about 10 seconds. And the way this process works is you grasp an object, you do your manipulation, and then you put it on a turntable, you record the entire thing, and then you segment these colored patches. And since we know the object geometry, we can do, using ICP registration and color map optimization, we can then reconstruct basically where the contact patches are on the object surface. Now, the big difference is that we also want that information for manipulations. So we're interested in something that works for information that like time series. So what we do is we record the start and the end pose of a manipulation. So we do this procedure twice. And then we can, for certain manipulations, it works to basically interpolate between the start and the end pose, between the start and the end contact locations. And by doing so, you can get so this would be like the start and this would be the end. And then you can interpolate between those. And you can get these moving contact during manipulation. So here, for example, if you pick up a flashlight and you rotate that, we can kind of approximate these movements of the contact patches on the flashlight like that. And then we can use this information again in simulation. And that's what I mentioned earlier. It's sort of independent of your manipulator, is that we recorded this information using a human hand, and we but we can transfer to, for example, here in this case, a 3-fingered gripper, right? That's not anthropomorphic. And what we did here is we just learned our reinforcement learning policy, where this hand is basically trying to match the contact locations over time. And the interesting part here is that we never encoded a rotation in our reward function, but the rotation is implicitly encoded in the contact information. That kind of gives you like an idea of how rich or how much information is implicitly encoded in those contexts and why they're so valuable for us. But yeah, I think we're already past 9, at least here on the East Coast. So I think we covered a lot of grounds today. A lot of different topics. I didn't talk about fabrication. We're working on that, and I in the future I would love to give a talk about that, especially about maybe how we can automatically fabricate soft robots by printing them directly from soft materials. But I think that's gonna be for another day. Yeah, and so I would like to open up maybe the discussion, and yeah, if you have more questions, feel free.
Okay, yeah. Thanks a lot, Dominic. That was a really insightful presentation. So now, if anyone has any questions regarding anything, you could ask now.
So, like, if there was a situation where you don't know the object's properties, and what if you want to apply some minimum amount of contact force so that the object doesn't plastically deform? So, uh, how do you, like, what would you do in that situation? What parameters should be considered in that situation?
So I guess say you have a delicate object, right?
Yeah.
Because I mean, so in general, this applies, I would say, to objects that you don't want to like squish, right? In that case, I think it really the same principle applies, right? So you really can't squish objects too hard, or you really can't. I mean, you really the hands are so soft that even if you contract the tendons, as long as
There
you're
is
not,
no
of
hard
course.
contact.
Sorry.
There is no hard contact, if that's what it means.
Yeah. No. So say even if you try to grasp a really soft object, as long as the object is not softer than polyurethane foam, I think you're not gonna be able to squish the object unless you really contract the tendons extremely hard. So I think the approach is generally, again, to find the easiest, most simple approach would be to find a pose that approximates the grasp that you want to do and like the shape of the object most closely, and then just contract the tendons to that pose, right?
Oh,
And the foam, just like the foam is really soft. Like it's so unless you want to grasp some, I don't know. Yeah, I don't know. I can't even think of something like. I'm sure there are. Maybe you have something in mind. I don't know.
yeah, if the object's stiffness value is very low, and we don't want to deform the object plastically. So, what amount of contact forces must be applied, as in to uh, stabilize the grasp without
Well,
deforming?
so again, there's almost no way for us to predict contact forces because it's just
Exactly. Yeah.
yeah, no. But so what kind of materials are we talking about? Like, do you have? Can you give an example? Just for me, I have a hard time to do. to imagine where this could be an issue.
So I think Apurvi are talking about the same kinds of materials that are used here, polyurethane foam, right? Or some other different kinds of materials as well.
Yeah, the same materials. Yeah.
Also, we're talking the same like a polyurethane foam or something like that, right?
Yeah, yeah.
Yeah.
Okay. I think in that case, I mean, you really don't have to worry about that. I would say that I would just apply a conservative amount of contraction, and then the hand will deform. And if you, I think the if you're conservative with your tendon contraction, the amount of force that you will apply is already capped at the stiffness of the foam. And so if you have a really, really soft material, you could use a softer foam, right? So maybe you can always, there are different types of foams, right? So for the applications or for the grasps that we used, especially for rigid objects or for the objects that I showed, we found that a certain stiffness and density of the polyurethane foam worked best. But I think in that case, I would try maybe if you're squishing objects because the materials or the objects that you're grasping are even softer than what your gripper is, then maybe you can use even softer polyurethane foams, right? That might be a way to ensure that you never really exceed a certain threshold in terms of force. That I think that would be maybe a good idea to do that.
Yeah. Yeah. Also, one more question I have regarding the data sets of pre-graphs you have uh, created. Like, how do you create the data set of the pre-grasping of many objects? Pre-grasp points, point clouds as such.
Are you referring to which are you for for the tendon optimization or for?
Graphs, first just stabilizing the grasp, like learning how to control the grasp. Your
Oh
like your
yeah.
brain.
So right. So how we transfer the grasp from the actual hand to the simulated grasp? Is that what you're? So
Like,
how we transfer that is. Oh, sorry.
yeah, you can please go on.
Oh, so what we do is basically we know and so for our human hand and for the cyber glove we can do we can do forward kinematics. So if we know the joint angles of our hand, we know we can get
Pose
we
of
can
the
extract the position of the fingertips, and we can extract the pose of the hand. And so what we did in simulation is basically we enforce basically as constraints, we enforce the same pose of the hand in simulation, right? So you can do that. And then the question is what tendon routing do you need, and what contraction do you need to achieve the same pose?
Yeah.
Yeah.
Yeah, I'm done. Thank you. Thank you.
Yeah, you're welcome.
Okay, does anyone else have some questions as well?
Hello, am I audible?
Yeah, you're audible.
Okay. Hi, Dominic. One thing that I found really fascinating was that with the contact patch information, you could show that the object was being rotated. That was actually very impressive to see. So, can you maybe, so this is a two-part question. Maybe first would be, can you maybe expand a bit on how you use reinforcement learning to achieve that simulation? If I found that correctly. And the second question would be, uh, what if we have the contact information for known objects that we probably do human manipulation on, do we also is the intention also to extrapolate contacts on objects that have not been manipulated by human beings for maybe novel shapes or novel maybe different dimensions? So extrapolation of contacts, is that also in the planning in the future, so as to help soft robots have a more informed pose on grasping new objects?
Yes. So yeah, great questions. So about your first question about reinforcement learning, the setup is basically it's a very simple setup just to kind of develop the idea of whether this can actually work. And so the simulator that I showed is the sofa simulator, and the way we frame this is we have a predefined design of a soft hand, and we also have a predefined tendon placement. So now in terms of that, there's nothing happening there. And then in terms of observations, the robot knows basically whether either one of the fingers is in contact or not, and it knows the position and basically it knows the pose of the object, and we encode basically the distance of those fingers to the individual contact points, and as actions it can take, it can contract the tendons to create motions. And then we just use we use stable baselines, PPO implementation, just to kind of see what it can learn with that information. And then in terms of extrapolating contact information to other objects, I think I don't think that that's the goal for us, simply because, so say if you have this information for a cube, or the soft hands can generally deal with a really, really large variety of object sizes. So say you have a cube-shaped object, your hand, the implicit or the compliance will already extrapolate for you by quite some large margin. So I think the goal for us is if you collect enough basic shapes, and if you collect enough types of manipulations on, say, like primitive object geometries, or like sort of if you've collected maybe the information about, say, a banana, then it should work for almost any other type of banana using a soft robot, simply because the compliance of the soft robots will be able to deal with these variations in maybe slight variations in shape and geometry. So I think the immediate goal for us isn't to really extrapolate between different geometries or shapes.
Got it. Thank you, Dominic.
Yeah, you're welcome.
I would like to just discuss something. So I recently watched a video on YouTube of like a 2 minutes paper. So there is an AI for virtual fingers. Like the AI guesses like it interprets the object, and then it grasps the object like that. So you can see that and use it in your research, like that thing. Like it uh, it detects the object, and it rolls the finger around that object and grasp it accordingly.
Yeah. I don't know what you're like, what specifically you're talking about. I don't think I have seen that research.
Could you maybe tell the name of the paper or the resource that you referred to?
Yeah, I think that would be great. Yeah, if you can just
So
post like
where I
either.
can share,
You
I
can
will
share it
that,
in the chat room. I think that would be good.
Yeah, I think that would be great. Yeah.
I will share that.
Yeah, in there's a channel called chat room in the lobby section itself. Yeah, meanwhile, if anyone has any other questions or comments.
Yeah, I mean, we can also talk in general about like soft robots or other robots or yeah, whatever you want to know in terms of manipulation, maybe. I don't
Yeah.
whatever you're interested in.
Yeah, any other comments regarding soft robots in general? Maybe some of the things that we talked about last time, if you want to, get Dominic's view, because he is actually, he is an expert in this field, so he can answer things in a more better way. So you can go ahead. Or also regarding generally PhD at CMU, or some other general questions that you want to ask or talk about, I think just now would be the time.
Hello, Dominic. Akshay here.
Yeah.
I have one question. So, when you look into this tendons placement, so what I realized is that the obvious challenge is that when you pull that thread altogether, it's the point where force is applied is actually the point where thread is connected, not the part where it is moving, right? So do you guys actually calculate the force at on those joints, or it's while stitching the tendon you straight away look at the simulation and based on that it is stitched?
Yes. So basically the forces that are created by contracting those tendons. So basically what happens is the skin, the soft layer, the outer layer of this hand is basically deformed or pulled on, and then because the outer layer is connected to the foam core, it kind of pulls the foam core into a certain shape. Again, there are no joints, so we can't estimate any force, or we can't really estimate any joint displacement. So what we do is
So it also depends on how good
yeah.
of a how to put it, how good of a friction we are getting between the object at the point of contact, object and the actuator altogether. Can I assume that?
Yes, of course. So friction between object and in general, or like robots in general, if you in terms of manipulation, friction is a very, very big factor of whether you can successfully manipulate an object or not, or whether you drop it. So that depends on basically the surface material of your object and the surface material of the hand. And in our case, we're using some textiles. So yeah.
So one question that I have is, do you think adding a skeleton or a rigid core to the hand could offer some advantages, or I think you purposefully chose it to be fully soft, right?
Yes, yeah, that's a good point. So I think that there's pros and cons here, of course. I think if you add joints, or if you add like a skeleton structure to those hands, you lose some of your compliance, you lose some of your softness. But of course, in terms of maybe achieving more grasp strength, that would be definitely beneficial. Also, I think if you would add a skeleton, you might be able to approximate at least maybe joint movements. If you say you had some bone-like structure inside your hand, then this might be more easy to kind of approximate your deformations. So I think that in terms of grasp strength and maybe also in terms of predicting motions and deformations, that might be beneficial, but with the downside of losing some compliance, and also it's quite difficult to even embed like a skeleton structure, because if you think about it, you would have to do that during the casting process. So it's actually it would be quite difficult to have internal structures inside the foam. That would like further complicate the fabrication process by a lot.
Actually, with the Baymax research that we were looking at from Professor Chris Atkinson, right? So there we saw that actually the structure, they do have a structure, although that is also something that they've put to an argument that whether we need it or not. But they said that if you need a structure, it should also be compliant, so to say. So the structure should not be rigid, and it was also pneumatically controlled. So maybe like for a hand as well, a semi-rigid structure or a compliant kind of a structure could actually maybe make the process of control a bit easier. I mean, it's a trade-off, right? The control thing and the flexibility.
Yes, yeah, absolutely. I mean, I think that, again, yeah, as you said, the internal skeleton doesn't have to be fully rigid. You could use some like slightly more rigid materials, or slightly denser materials than foam. And using that, you can also, I mean, the big advantage would be to be able to kind of have targeted places where the hand deforms, instead of right now, if you have this fully compliant thing, then once you pull on a tendon, the whole core, the whole thing deforms. And whereas if you have a skeleton, you could kind of get these more targeted deformations where you actually want them to be. So in terms of finding a design, finding like constraining the motions that you want, that would maybe help with that. But again, you might lose maybe in terms of compliance, which then if you want to grasp something, or if you want to do manipulations that might harm you in down the road.
And are there any specific applications you're also targeting? Because this is a very new research, right? Still a lot of industrial use cases are probably need to be figured out, or what is your take on that?
Yeah, so I mean, in general, there are lots of different applications. The one of the obvious ones is, I would say, in human robot interaction. So for example, in so we're looking at using that as for prosthesis, but also for like hair robots, but then also for maybe thinking about manufacturing, everywhere where you have some delicate handling, like also like packaging, wherever you have like delicate materials that you don't want to get harmed. That could be of use. And then maybe for agriculture. And I'm sure there are lots of other applications out there. Yeah.
Dominic, I have one question. So, actually now, because after listening to all your points, I actually got biased towards tendons placement. So, is there any other way of actuation apart from tendons?
Oh yeah, yeah. A good question, because so today we only talked about tendon-driven soft robots, and right, there are a number of different ways to actuate soft robots. One of the most important other option is to use pneumatics, and like these inflatable robots. I think you've probably all seen that. And then there's also I think electric piezoelectric actuation. I've seen I think I've seen thermally activated metals, for example. But I think the most important ones are pneumatic and tendon driven. And I think the main difference between pneumatics and tendon driven is really that for the disadvantage of using pneumatics, I think the big disadvantage for me is that in order to be able to inflate the actuator, you need space. So so there's a limited amount of actuators that you place, and when you place them, you need space for the actuator to actually inflate. Whereas for a tendon, it doesn't. You can place that anywhere on the hand, and the contraction doesn't need it doesn't inflate, or it doesn't. It's a much more flexible way, I feel like, to place actuation or to induce actuation. Of course, the advantage of pneumatics is that, I think the main advantage with pneumatics is that you can have multiple chambers that you inflate, and then with the same pump. So you have maybe one pump, and then you can inflate a number of different chambers and create deformation doing that. But I think the disadvantage of inflatables for me is really that, well, first of all, you need a pump, then also usually it's quite noisy, or pneumatics are at least somewhat noisy. And once you have a design, you can't just change like the placement of the bellows. You have to change like the entire design and figure out the placement. Whereas for us, I think we can fairly easily change the placement of tendons by just sewing in new tendons, or so that makes it much more flexible.
And so while placing all the tendons, do we keep any kind of restriction, or is it okay to think of having multiple tendons to even a single finger? Let's say that if I put multiple tendons to a single finger, that will lead to a better control altogether.
So yeah, no, there are really no restrictions. I mean, of course, you can definitely end up having combinations that don't make sense. For example, if you think about a finger, a good way to think about it, if you, for example, place 3 tendons around one finger, in like a rotational difference of like 120 degrees. So basically, if you have, say you have a circular finger, and you place 3 tendons around this finger with a angular difference of like 120 degrees, then you can really kind of think about actuating this. You will be able to actuate the finger in any kind of direction by using like some sort of linear combination of 2 or 3 tendons, right?
Yes, actually, the reason I asked you this is because, as you said, 3, right? I was actually imagining single finger being controlled by at least 12 tendons. Three tendons connected at 4 different points. So basically, on your tip and then the next 3 joints.
Yeah.
Okay.
Well, again, we don't have joints.
I'm like, idea is to no, you don't have a joint in your palm, but if you want to have a control that precise, that so basically, so if you replicate that soft robot's finger with your own finger, then you can see at least 3 joints in a fingertip, right? So
no, I mean, you can't really replicate. I mean, you can, so you can. No, I think so. I think the deformation will be very continuous, and will really depend on the thickness of the foam.
Okay.
So if you have just one, if you think about it, if you have just one finger, the deformation will be entirely dependent on the surface area, or like basically the surface area of and the thickness. You could have locally change the thickness of the foam, and by that maybe induce some more contraction than in other parts. But if you just have one circular, like a cylindrical shaped finger, then the deformation would definitely not be joint-like. It would be more like a continuous deformation.
Yes.
Yeah. Thanks, Akshay, for your question. And so the video that Shaurya was talking about, he has shared on the chat room already. Maybe I can share my screen and play the video.
Yes, yeah, sounds good.
Dear fellow scholars, this is 2-Minute Papers with Dr. Károly Zsolnai Fehér. Today we are going to see...
Can you hear the audio as well?
I don't see your screen.
Oh, okay.
Oh, yeah, now I do.
Okay. Yeah, I think. Just wait a minute. No, yeah. So I think I'll just play it here itself. So.
How we can use our hands, but not...
Now it's visible, right?
Yeah, I can hear the sound.
Okay.
...our fingers to mingle with objects in virtual worlds. The promise of virtual reality, VR, is indeed truly incredible. If one day it comes to fruition, doctors could be trained to perform surgery in a virtual environment, expose astronauts to virtual zero-gravity simulations, work together with telepresence applications, you name it. The dream is getting closer and closer, but something is still missing. For instance, this previous work uses a learning-based algorithm to teach a head-mounted camera to tell the orientation of our hands at all times. One more paper down the line, this technique appeared that can deal with examples with challenging hand-hand interactions, deformations, lots of self-contact, and self-occlusion. This was absolutely amazing because these are not gloves. No. This is the reconstruction of the hand by the algorithm. Absolutely amazing. However, it is slow, and mingling with other objects is still quite limited. So, what is missing? What is left to be done here? Let's have a look at today's paper and find out together. This is its output. Yes, mingling that looks very natural. But what is so interesting here? The interesting part is that it has realistic finger movements. Well, that means that it just reads the data from the sensors on the fingers, right? Now, hold on to your papers and we'll find out once we look at the input. Oh my! Is this really true? No sensors on the fingers anywhere. What kind of black magic is this? And with that, we can now make the most important observation in the paper, and that is that it reads information from only the wrist and the objects in the hand. Look, the sensors are on the gloves, but none are on the fingers. Once again, the sensors have no idea what we are doing with our fingers. It only reads the movement of our wrist and the object, and all the finger movement is synthesized by it automatically. Whoa! And with this, we can not only have a virtual version of our hand, but we can also manipulate virtual objects with very few sensor readings. The rest is up to the AI to synthesize. This means that we can have a drink with a friend online, use a virtual hammer to, depending on our mood, fix or destroy virtual objects. This is very challenging because the finger movements have to follow the geometry of the object. Look, here the same hand is holding different objects, and the AI knows how to synthesize the appropriate finger movements for both of them. This is especially apparent when we change the scale of the object. You see, the small one requires small and precise finger movements to turn around. These are motions that need to be completely resynthesized for bigger objects. So cool. And now comes the key. So, does this only work on objects that it has been trained on? No, not at all. For instance, the method has not seen this kind of teapot before, and still it knows how to use its handle and to hold it from the bottom too, even if both of these parts look different. Be careful though, who knows, maybe virtual teapots can get hot too. What's more, it handles the independent movement of the left and right hands. Now, how fast is all this? Can we have coffee together in virtual reality? Yes, absolutely. All this runs in close to real time. There is a tiny bit of delay though, but a result like this is already amazing, and this is typically the kind of thing that can be fixed one more paper down the line. However, not even this technique is perfect. It might still miss small features on an object. For instance, a very thin handle might confuse it. Or if it has an inaccurate reading of the hand pose and distances, this might happen. But for now, having a virtual coffee together, yes please, sign me up. This episode has been
Yeah. Okay. Yeah, then thanks a lot, Dominic. I think this was a really nice session that we had. We talked, you shared a lot of details about your research, and I think everyone also followed it and was able to understand it, and it was and a very engaging session overall, and that was followed by a Q&A session where I think we also discussed about your research, the soft robotics area from other different perspectives. So overall I think it was really a fun session, and we are always open to have you again, Dominic, and you could talk about the fabrication part or any other aspect of the research that you make progress in the future. So yeah, thanks a lot, Dominic, and for everyone else who participated and joined today's session.
Yeah.
Yes,
for-
thank you.
for
It was
having
a
me.
great session.
Yeah, I think I had a lot of fun. It was nice to see that you were interested in what we do, and I'm happy to, in the future, give another talk about any progress that I make. And yeah, hope you learned something, and I hope you have a nice weekend.
Yeah, for sure, definitely. Thank you everyone.
Thank you. All right. Bye.
Bye.
Bye.